In this video, I know I said I was going to do a type 3 problem, which I will, but there's actually one more type 2 problem in your PowerPoint, and some of you might not need to see this, but I just thought it would be a good idea to do one additional type 2 practice problem, just to sort of review that as you're watching before I jump into what I call the type 3. So you can fast forward through me doing my type 2 if you feel really confident with that. So just as a reminder, when we're doing these vertical motion problems, I was classifying them into types. And so what I call a type 1 is something with an initial velocity of 0 that simply falls down. What I'm calling a type 2 is something that goes up and down under the influence of gravity, but it's going to be symmetrical. So like I throw it out of my hand, it lands back in my hand, or it leaves the ground, comes back to the ground, that sort of thing. And then the type 3 problem is the one that lacks the symmetry, okay? So there was one more type 2 problem, and I forget the initial velocity. It was either 5.25 or 5.5. I'm just going to go with 5.25. So if it's slightly different from your notes, I'm sorry. And so the problem says something is thrown up with an initial velocity of, let's say, 5.25 meters per second, and you are asked to find total time in the air and how high the ball goes. Sometimes they call this projectile, how high the projectile goes. Okay, so for the type 2 problems where they're nice and symmetric, this thing is going to go up and it's going to come right back down. It's going to land at the same position. And so when you do these problems, just as a reminder, you only need to list your givens for up or down. You don't need to have both. You can, but it's going to be sort of redundant because of the symmetry. Everything's going to be the same. So distance up is going to be equal to down. Time up is going to be equal to down, so on. So when we're going up, I'm going to list my givens. V naught, B, A, y minus y naught, and t, and notice again, I did this in class the other day, where I write t, I'm going to write t up. That's a good way for me to remind myself this is only half of the time. So if I throw the ball or the stone, I forget what it was in the problem, up with an initial velocity of 5.25, that's what goes here for my v naught, 5.25 meters per second. And for all of these problems, no matter what type, if they're vertical motion problems, we know that acceleration is a nice negative 9.8. Again, remember it's negative because the Earth is pulling it down. So even though the thing is going up, because I threw it up, Earth is pulling it down. It's accelerating it in the downward direction. Okay, so as it's going up, we said Monday in class, the key to solving this problem is at the very top of its path, it stops for a brief moment in time. So the final velocity of going up is 0. And now we can use this information to solve for the rest of what they asked for. So if they're asking me to find my maximum height, and I don't know time yet, so let's just solve it in that order. So if I don't know time yet and I want to solve for height, I'm going to use the third kinematic equation because that's the equation with no time in it. So I'm going to say v squared is equal to v naught squared plus 2a times y minus y naught. Before I do any real algebra, I want to cancel out any zeros. And so I know that the final velocity is 0. I'm going to make that side 0. And I want to solve for, again, this vertical displacement. So I'm going to subtract v naught squared from both sides. So this is negative v naught squared is equal to 2a times y minus y naught. And now I'm going to divide both sides by 2a, and that's my answer. Now, of course, we want to put some numbers in there, but y minus y naught ends up being equal to negative v naught squared over 2a. So we plug our values in. This is negative the quantity 5.25 meters per second squared over 2 times negative 9.8. And so we have, just like Monday in class actually, we have a negative divided by a negative, which gives us a positive, and that's a good way of checking your work. So the signs are actually really important. These are vector quantities. I need to see those signs correctly placed in there. And the fact that I end up with a positive y minus y naught makes sense because I'm going up. So my displacement is going to be in the positive direction. And so the value we get for this is about 1.4 meters. So maximum height is about 1.4 meters. And then the second part of this problem asks you to find the time that it's in the air. So I'm going to solve for time. We just, again, really similar problem Monday. I would go with the first equation and solve for time because it's just easier. It's a shorter equation. So So I'm going to say v is equal to v naught plus a times t. If I'm looking at up only, I'm just going to solve for time up. The final velocity going up is 0. So I have negative v naught is equal to a times t up. So time up is equal to negative v naught over a. So v naught, again, is negative 5.25 meters per second divided by a, negative 9.8. Again, I have a negative divided by a negative, which is going to give me a positive time. Remember we talked Monday about how you always want to see those positive times. And it's a little over half a second, 0.54 seconds. So if I wanted to know my total time, which is what they asked me for, I'm going to take that time up, 0.54 seconds, and I'm going to double it, right? So this is what, like 1.08 seconds. So my total time in the air, again, this is still at type 2, is equal to the time up doubled, or time up times 2, of course. And that's it, right? So that's just another example of a type 2 to warm ourselves up. Now, a type 3 problem. I'm looking for my eraser, which my kids apparently have moved. Lovely. I'll just use a rag. A type 3 problem is one in which you lose the symmetry. Sorry, I can't even find a rag. And so your up and down are no longer equal. Here we go. It was covering a baby, if you're curious. Not a real one, baby doll. So the one in the notes says that we throw something up. It actually has a really small initial velocity. So we throw something up with an initial velocity of 2 meters per second. It's just like a little light toss, that kind of a value. So we throw something up with an initial velocity of 2 meters per second from a height of 1.2 meters. And then we're going to solve all kinds of things. We're going to find the total time that it's in the air. We're going to find its maximum height above the ground. And we're going to find, I think I said, its final velocity. So type 3 problem, I'm a more visual person, so it's kind of helpful for me to sketch it out. So I wrote y naught is equal to 1.2 meters, just meaning I start at this initial position of 1.2. I'm not going to actually put it in the equations that way. You can. You're going to see me do it a little bit differently. And again, that initial velocity is 2 meters per second. So if this is the ground, it's amazing drawing, but this is your ground, and this is that 1.2 meters per, meters, just a height. It's as if I throw something from this initial height, it goes up a little bit, and it's going to come back down to the ground, right? If these numbers were bigger, if I were throwing something with a bigger velocity, like 10 or 20 or even 100, and I were throwing it from a greater height, the differences between up and down would be much more dramatic. So a lot of these type 3 problems give some more dramatic differences. So when you're solving these problems, they're not hard. It's not going to be any harder than what we've been doing. What I would say is they're tedious. So because you lose the symmetry, time up and time down are no longer the same. Distance up and distance down are no longer the same. And so it just takes longer because you can't make those assumptions. So the first thing you have to do that makes it take a little bit longer is you need to write your set of givens for up and for down. So when I do a type 3 problem, you always see me list y up and y down. And we list those same givens we're used to. So v naught, v, a, y minus y naught. And then I write the t's as t up and t down. Okay, so let's go through the generalizations you can make for a type 3, and then we'll solve the specific one. So for a type 3 problem, like any other vertical motion problem, we always know that acceleration. Again, it is negative 9.8. Galileo proves that to us. We're going to try his experiment a little bit ourselves at home next week, see if we can see what he says. But no matter what he says, the acceleration is negative 9.8, as long as we're ignoring air resistance. So for both sides of my givens, or both lists, I can put that value in right away. The other thing I can assume is for anything that's going up and then coming back down, it stops at the top of its path. We talked about that. When it has that moment where it changes direction, the apex of its path, it's going to stop for a brief moment in time in y. And so knowing that, we can say for every type 3 problem, at the very top going up, the final velocity is 0. So we can always, for y up, say final velocity 0. And then coming back down, that means the initial velocity where we start to go down is 0. So no matter what your type 3 problem, like what the initial conditions are, this stuff we know to be true, okay? Now, let's go back over to what this specific problem says. I throw something up from a position of 1.2 meters, and it's going to come back down, and I throw it with an initial velocity of 2 meters per second. So that initial velocity, 2 meters per second, goes right here. It's the initial velocity with which I throw the ball, or whatever it was, up. And so the question asks me to find my total time in the air, maximum height above the ground, and final velocity. Okay? So maximum height. To find maximum height, I need to find how high it goes. Now, I'm not doing anything with that 1.2 yet. I will, but not yet. So I'm just leaving this as is. If I want to find total time, then I need to find time up, and I need to find time down. And then if I want to find final velocity, that's this thing right here. Right, coming back down, the final velocity. Okay, so let's start to solve it. When you're going in to solve these problems, you want to look at, in your sets of givens, what do you know the most about, up or down? And in this case, right now, I know the most about up. I've got 3 givens for up, I only have 2 for down. So I'm going to start with up, and really to solve this problem, I need to find y minus y naught and t. I need to find both of them. So we can take them in any order. I'm going to do the reverse of what I just did, just to make it a little different. I'm going to solve for t first. So if I want to solve for t, right now I could use this first equation. I know enough about it to solve for t. So I'm working in y up, and I'm going to say v is equal to v naught plus a times t. So if I think about those givens for up, the final velocity is 0. And so I can move things over. I can say negative v naught is equal to a times t. I can divide both sides by a. And so I can say t up is equal to negative v naught over a, which is negative 2 divided by negative 9.8. And so when I plug that number in, it's going to be a very small time. Again, I use pretty small numbers on this particular problem. I get about 0.204, so let's say 0.2 seconds. So the ball is only going up for 0.2 seconds. Really short amount of time. And then we want to find how high it goes. So if I want to find how high it goes, and actually I know the time, I'm going to go with the second equation here, just because it's already solved for. I don't have to do any algebra. I can plug and chug. So again, I'm still thinking about y up. I'm going to say y minus y naught is equal to v naught t plus 1/2 a t squared. And I can just plug and chug. So v naught is 2 meters per second times the time, which is 0.2 seconds, plus 1/2 times negative 9.8 times 0.2 seconds squared. And remember, I'm just squaring that time. And when I put those in, remember this it's kind of maybe hard to see on the board, but the 1/2 times negative 9.8 times 0.2 times 0.2, this value is negative. So it's like I'm taking the 2 times 0.2, and I'm subtracting. So just be careful with your signs when you do that. So let's see what I get. It's going to be quite small again, because I really barely threw it. So how high does it go? It goes 0.2, that's kind of funny. I forgot about the symmetry on that. That's just like happenstance, of course. So don't bank on that happening. So the height it goes up is 0.2 meters. Now, it goes 0.2 meters up from where I threw it. This is not drawn to scale. But on my little diagram, it starts 1.2 meters, and then it goes up from there 0.2 more, okay? And so we need to use that to think about the down part of this problem. So right now, as it stands, we solved for everything with y up. I really haven't introduced anything new there. I'm going to erase my y up work, and let's go deal with the down. Okay, so the key is that, like I said on my picture over here, I start at 1.2 meters and then I go up 0.2 more. So I have to come back down that whole distance. So my displacement down, this y minus y naught, is negative because it's falling down. And it's going to be the 1.2 meters where you started plus the 0.2 you went up. And again, you want to make that negative because it's falling down, okay? So I would call that, I'm going to erase it so I have more room, negative 1.4 meters. And now that we know that, which we had to do all this stuff with up to get it, now that we know this, we can solve for everything else with y down. So we can find the total time, we can find the final velocity. Let's go find time first. So if I want to find time and I don't know my final velocity yet, and I have this list of equations kind of in front of me, I'm going to go with the second equation. The second equation does not have final velocity in it. So I'm working with y down now. And I'm going to say y minus y naught is equal to v naught t plus 1/2 at squared. Now, coming down, the initial velocity is 0. So v naught t cancels out. So I'm left with y minus y naught is equal to I'm just going on autopilot and writing the whole thing, is equal to 1/2 at squared. I'm going to multiply both sides by 2 to lose the 1/2. I'm going to divide both sides by a, and then we have t squared, so I'm going to take the square root of both sides. So t, and this is really t down, ends up being the square root of 2 times y minus y naught divided by a. Now, I'm about to put my numbers in, but let's think about it. It went up for 0.2 seconds. It's coming back down a longer distance or a greater distance. And so what I'm expecting to see, a good way to check yourself, I'm expecting to see that my time down is a little bit greater than my time up. Now again, here I was using pretty small numbers, 1 and 2, right? So there shouldn't be a dramatic difference in this case. But if I get time down to be bigger than 0.2, I should feel pretty confident about my work. So let's put that in. So we say, okay, time down is the square root of 2 times y minus y naught, which is negative 1.4, divided by a, which is negative 9.8. This works out nicely with our signs. The negatives cancel out. And this gives me, let me tell you, 0.53 seconds. So looks good, right? This matches up with having a time down that's going to be greater than my time up. And so to get my total time, I simply add those two numbers, 0.2 plus 0.53. And so my total time that the ball is in the air is 0.73 seconds. And then the final thing I can do is find my final velocity. I know everything else. So to find final velocity, if I look at my list of equations, the first equation is the shortest. It's just going to be plug and chug. So I'm going to use that. I'm going to say v is equal to v naught plus a times t. Now I am just looking at the y down here. So I'm going to use my time down. I'm going to use my v naught for down, which is 0. So I'm going to say final velocity is equal to a, which is negative 9.8, times t, which is 0.53. I'm just using that time down. And so this gives me a negative number, which makes sense because it's falling down. I get about negative 5.2 meters per second. This conceptually makes sense because if it started with 2 meters per second, it's going up and coming back down like more than twice the distance, a lot more of the distance, then we expect it to be going faster, right? Because it's got a greater fall. So we wanted to see a number that was bigger than 2, and we do, so we should feel pretty good about our work here. Okay, so this is an example of how to work through a type 3 problem. Now, one thing I want to say, and this might seem confusing, and that's okay. Like, depends on where you're at in your math classes. So this next part, if you don't feel confident with it, for now, it's okay. You could, if you're looking at these equations, particularly the second one. So those of you in calculus will be working with this one a lot. you can look at the function for the whole motion. So for the whole up and down all together, you could put in your initial position, 1.2 meters. You could put in your initial velocity, you know your acceleration. And so like if you think about this one, that could allow you to solve for, you know your final position, sorry, y is 0 because you land back down on the ground. So you could solve for time, like as a quadratic, for example. I don't know if anybody was thinking of doing that. So there's different ways you can consider the whole motion. Even over here when we go to find final velocity, if I put in the initial velocity of the whole motion as 2, and the t is the whole time of 0.73, I should get the same answer here. So that is certainly something you may do. However, in physics, we're really into like the real physical quantities and what's happening here. And so splitting the motion up into up and down tends to allow you to find more of that, right? I can really figure out like exactly how high from the initial position did this thing go, or how much of that time was split into up and down rather than finding the whole time of travel. And sometimes that's really useful. So this is why you see me doing it this way, if that feels a little bit more tedious to you. Some of you who are more comfortable with like the function world can go at it, looking at it as just one continuous motion up and down. But there are times when you will need to do it this way because you're going to need to figure out information that's kind of in the middle. So be comfortable with problem solving the way I just did it. But just know that if you're approaching it differently, and you can, and it will give you the information you need, I am okay with that. Okay, so I'll stop here, and I'll see you in class tomorrow.